Hello, welcome to the last topic for this course, and it's actually a huge topic, so it's going to take a couple of weeks and a few videos. The topic is P versus NP, which is something that you've encountered in Competitive 5, Com 2010, but my guess is that it was done in the last week and the lecturer said that it won't be an exam, so I don't know how many students care about it. It's something that we introduced in that unit just in case students there don't take Com 3010, so at least they know about P versus NP, and some of you may think that that's a good idea by now. I mean, to put P versus NP in Com 2010, not to do Com 3010. But anyway, to the plan. I'm going to go over P versus NP informally in this lecture. Then next we're going to be doing NP completeness, reduction, approximation. Now, this probably won't make sense to you now, but it will, hopefully. Yeah, because for some of you this would be new. And P versus NP is like the end boss for this unit. Whatever we've done in previous weeks is actually building up to this topic. So let's look back a bit. In week 3, we talk about brute force methods. And generally, I think it's good to know how to do simple stuff like recursive backtracking. Because worst come to worst, you can always do brute force. And one important takeaway from that week is that hopefully you can see now how much work you have to do to solve something using brute force. Like how many combinations are there or how many permutations you have to go through. How big is your search space? How many recursions you have to do. And hopefully you learn that exponential complexity is just horrible. Of course, the focus then was to find overlapping subproblems so that we can do things much faster using dynamic programming. And you saw yourself that the running time of a brute force approach can go from minutes, like hours, often days, and then we write the dynamic programming implementation for it, and we can do it in seconds. That's because we often went from exponential complexity to just polynomial complexity. We often went from 2 to the n to n squared. So at this point, I hope that you're okay with exponential complexity. Like you've seen it, you played around with it, you improved it, and you understand that polynomial time is good because that's the running time of most of the dynamic programming algorithms that we did. But does this mean that every problem can be done in polynomial time? And of course, the answer is a big fat no. There are some problems that even when you can use dynamic programming to solve it, the complexity of the solution is still exponential. This was actually in one of the comic strips that I showed you earlier in the semester. It's one of my favorite ones. It's about the traveling salesman problem. Even with dynamic programming, the complexity of the solution is still exponential. We went from x factorial to n squared to the n, which is good, but that is still exponential. Okay, so we know that polynomial time is good. We call these guys tractable. Then we have the intractable guys. These are problems for which you don't know if you can do it in polynomial time. There's no such polynomial time algorithm to solve it. I just want to point out that not polynomial doesn't always mean exponential. It can be factorial, which is worse. It can also be a quasi-polynomial. Hope you remember seeing this like in week 1 or week 2. If you have n to the power log n. And you may have heard P versus NP before. I'm sure you have. But there's also something called QP, quasi-polynomial time. So these are the class of problems which can be done in quasi-polynomial time. In fact, there's a lot of these complexity classes. Here's a Wikipedia link on it. You can look for it. Look at all these complexity classes. Okay. The ones that we know, the ones that you've seen is, well, P, polynomial time, NP, and we're going to talk about NP complete and NP hard. But then there's NP easy, NP equivalent, there's PCP, probability checkable proof, P-space complete. I'm not sure what else I have heard before. Anyway, as you can see, there are lots and lots of complexity classes. But these are only relevant if you go really deep into complexity theory. The ones that you need to know, well, we went through it. This is probably an easier Wikipedia page for it. these probably look a lot more familiar, right? You got your O1, your log n, your on, and log n, n squared. And from this point on, is no longer polynomial. So here are the main ones that you should know. And I think sub-exponential is the only new one here. So think about sub-exponential as exponential, but slightly better because you're looking at n to the power of e, where is something small, like let's say a half. So instead of like 2 to the n, you can have 2 to the square root of n, right? It's still pretty bad, but not as bad as exponential. And these guys at the bottom here, we have a name for them. We call them super polynomial. Now, do you need to know these? Well, I guess these ones, yeah, it would be nice if you do. We're not going to be doing much work on it, but so at least just be aware that they exist. Understand that there is a world of complexities beyond polynomial, and you barely scratch the surface of complexity theory. I mean, we looked at time complexity here. This is stuff that you know, right? And then there is a whole lot more of complexity classes, which you haven't encountered yet. So yeah, just be aware that those guys exist. And in this course, really, we want to know if we can do something in P. That's really the main point. But understand that going from exponential to sub-exponential is actually still a big thing. You don't always have to come up with something in P. Okay. So again, yeah, these are the two we worry about. Well, in this next 2 weeks. And honestly, I don't think we can. I don't think you can go from exponential to polynomial. Well, we're going to talk about this later. But in reality, it's hard for people to even go from exponential to sub-exponential. So let alone going from exponential to polynomial. So you might be wondering, well, you kind of know about P versus NP. You might be wondering, well, why jump down from exponential to polynomial? Well, why skip exponential? So hold on to that thought for a minute. We'll get to there. We'll get there. For now, I want to ignore every other complexity classes except for these three. Oh, and you might be wondering, when we talk about complexity classes, are we talking about the problem or about the algorithm? Like, which one is in the complexity class? The problem or the algorithm? Well, actually, it's a problem. And we say that a problem is in polynomial if polynomial time is the best way we know on how to solve it. I mean, sure, you can do a problem in different ways. Let's say there's something you can do polynomial time, but you can also do it badly in exponential time. Well, that makes a problem in polynomial time still. Also, later you'll see a definition that will fix this. Because we can actually say that if something is in polynomial, then it is also in exponential time. Well, we'll worry about that later. But just understand that the focus is on the problem and not the algorithm. But you see how, at least to me, they're kind of the same thing, right? So if a problem is in polynomial time, that means there's an algorithm that can do it polynomial time. So is a focus on the problem or the algorithm? Well, they kind of one and the same to me. But you can actually prove that some problems must at least require this amount of effort. Like, you can say that some problem must be done in polynomial time. Like, so you can't do better than polynomial time. So what's a good example? I guess something like linear search. If the array is unsorted, you can say that you have to look at every element. So it must be done in ON time. You can't do better in ON time because you'll be skipping some stuff if it's not sorted. Yeah, I'm not sure that's a very good example actually, but you can actually prove that you can't do sorting better than n log n in the general case. So there's a proof of that in CLRS. But anyway, we can do this. We can say that some problems can only be done in polynomial time or in exponential time. We can prove that this is the best that we can do, right? I mean, if I have to go through a double array, then, well, that's have to be n squared. Now, proving that something must take at least exponential time is different to proving that something can be done in exponential time. That's the second point here. The first one is much stronger. It's saying that we can't do better. But just proving that I can do something in exponential time doesn't mean that's the best that I can do, right? It's not proving that this is the best I can do. It doesn't mean that I can't do it in sub-exponential time. It doesn't mean that I can't do it in polynomial time even. And that is where we at with p of NP. So let's say that I have a problem Q, and the best algorithm that I know that can solve it is exponential in complexity. Is there absolutely no way that I can do it in sub-exponential time? Or am I just too stupid to work it out? Same thing with polynomial time. Is there absolutely no way that you can do this in polynomial time? And that is the problem that some scientists have with some of these problems. So they got a problem, and they cannot show that the problem Q, say, can be done in polynomial time. They don't know any algorithm that can do it in polynomial time. But they also cannot show that Q cannot be done in polynomial time. So that's the frustrating bit. So to repeat, there are problems that are definitely exponential, as in you can't do better. But there's also a bunch of problems where we just don't know. Maybe it can be done in polynomial time. And let's define a few notations to make the explanation easier. So we're going to say exp is the class of problems that can be solved in exponential time. And p is the class of problems that can be solved in polynomial time. So these guys, exp and p, they're sets. And if you remember back when we discussed complexity classes, we also defined them as sets. So On squared is actually the set of all algorithms that have complexity bound above by n squared. So if something is log n, it is still On squared, because that's just the upper bound. They're sets, right? So same thing here. If Q is in P, then Q is also in exp. Because if you can solve something in polynomial time, then you can also solve it in exponential time. So, in fact, when you think about it, P is actually a subset of exp. As in, every problem that you can do in polynomial time, you can also do that in exponential time. So that's the notation you have here. P is a subset of exp. Actually, we should use the second one, because this one here is saying that P cannot be exp. So P cannot equal exp. Because we know there are problems that cannot be done in P time. So P and exp, they can't be the same set. Now, what I said in the previous slide, it's a lot easier to say now. I know that Q is in exp, and I want to know if Q is also in P. Hopefully that makes more sense now. But let's try if you're okay with this. Let's test your understanding. Suppose that Q is in P. Is Q also in exp? Well, the answer should be yes, right? If you can do if you can solve a problem in polynomial time, then you can also solve it in exponential time. So P is a subset of exp. So yeah, if Q is in P, Q is in exp. If Q is in P, is Q also in sub-exp, where sub-exp is the class of problem solvable in sub-exponential time? And again, the answer is yes. If you can solve something in polynomial time, then you can also solve that in sub-exponential time. Because again, P is a subset of sub-exp, sub-exponential time. Right? All the problems that you can solve in polynomial time can also be solved in sub-exponential time. Now, let's say that Q is in exp. Is Q also in P? Well, can you prove it? You need to be able to solve the problem in polynomial time. Maybe it is, maybe it isn't. Right? So hopefully it's clear about the idea about complexity classes, P sub exp and exp. And we know that this is true. We know that P is a subset of sub exp, and they're not the same set. So there are problems that you can solve in sub-exponential time, which you can't solve in polynomial time. And same with exp here, there are problems that you can only solve in exponential time. So this is always a bigger set than exp is a bigger set than the sub exp, and it's a bigger set than P. Now, what we're going to be doing today, well, for the next 2 weeks, we're going to study another class of problems called NP. So you know what complexity classes are now. It's just a way to classify problems. So we're going to study a set of problems that have a different behavior. It behaves differently from P, behaves differently from exp, behaves differently from sub exp. And it does not stand for non-polynomial. Like the most common mistake that I hear is that people say P, NP, P plus NP, NP means non-polynomial. So everything which is not polynomial. That is not true. NP stands for non-deterministic polynomial, but that's another definition. Let's just go with the informal definition of what NP is for now. Okay, so this is a special class of problems in which you can't solve them in polynomial time. Well, as in, you don't know if you can solve them in polynomial time, but so far there are no polynomial time algorithms to solve them. The thing is, if you do have a solution, then you can verify that in polynomial time. You can check whether the solution is right or not. And that's kind of why that's special. If you give me a solution, I can check whether or not it's right in polynomial time. So can I make a solution in polynomial time as well? It seems like, I don't know, I look at my code, it runs in polynomial time to check the solution. So can I modify that code to produce the solution instead? And also in practice, the problems that you see, they're very similar to problems in P. The example that we have here, is a shortest path and the longest path, and Euler cycle and a Hamiltonian cycle. So you've seen Euler cycle in Com 225, Com 2010, but you probably forgot about it. But at least shortest path and longest path, you know. And we've done a lot of shortest path. And when you think about longest path, well, that's a very, very similar problem. So how different can it be? Well, it turns out that there is no polynomial time algorithm to work out the longest path in a graph. Let's take a small example. So let's take a graph where all the edges have the same weight. And let's say we're trying to find the shortest path from these two, from source, the purple node here, and we want to go this side of purple node. If I ask you to work out the shortest path, then it's easy, right? You can spot that in a second. Just go maybe 1, 2, 3, or 1, 2, 3. I think that's the one that I chose. Yeah, 1, 2, 3. And there are many combinations, but when I see that, I mean, it seems easy. It seems easy to just picture the shortest path there, and it's quick to verify as well. But when I ask you, give me the longest path, maybe it will take you longer to work it out. So there's a path that actually goes through every single vertex. And by the way, generally when we talk about longest path, we say it's a simple path, as in you can only visit each vertex once, otherwise you have a cycle and you keep on going. But anyway, even with that limitation, there's a lot more options. So hopefully you have the intuition that this is harder. And in fact, we discussed this a while ago as an example of a problem with no optimal substructure. So we pretty much have to brute force to find the answer. But the thing is, if I tell you that I know the longest path is of length 5, let's say I know this, and I give you a solution. So, hey, here's a bunch of edges, and I know that the longest path is of length 5. Can you just check if this is a correct solution? Well, that would be trivial, right? Just make sure that you have a path from the source and it actually goes to the destination. Make sure you only hit every vertex once, and make sure you have 5 edges, and you're done. So both problems, if you have a solution, you can verify it in polynomial time. Well, in fact, with the shortest path, you know you can do it in polynomial time. But the longest path, it can't be done in polynomial time. But with if you do have a solution, it's easy to verify. So the next problem is the Euler cycle versus the Hamiltonian cycle. An Euler cycle is a cycle from one node going back to itself that uses every edge in the graph. So actually, I guess I don't need a second node here. Okay, so let's say we want to go from this purple node back to itself using every edge once and only once. Can you find a path that does that? Well, I'm just going to draw it here. Well, actually, yes, you can. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You use every single path. You're allowed to visit a vertex twice. It's just that you must use every single edge once and only once. So it's like drawing the shape with a pencil without lifting your pen ever. Can you do it? So that is actually not so hard to do, and probably not going to discuss it again in this unit, but you did that in Comp 5, Comp 2010. And it's just about counting the degree of each node, basically. So this can be done in p time, in polynomial time. Now, Hamiltonian cycle, very, very similar. You have to start and end at the same vertex again, but now you're only allowed to visit every vertex once. Can it be done easily? Well, let's try 1, 2, whoops, no. So for example, this is a bad path because I'm stuck in this one now. Like I go there, and now I can't go back to the starting node because, well, we'll have to visit a vertex twice. Is there a solution? Well, yeah, there is a solution. This one. Just to be clear, you don't have to use all the edges. Actually, you can't, because you can only visit each vertex once. So if you have a vertex with 4 edges connected to it, you can't use them all, because that means you have to visit the same vertex more than once. Now, this may surprise you, but Hamiltonian cycle is actually harder than Euler cycle, in that there is no polynomial time algorithm to solve it. But can you see that? I mean, not me at first. I actually thought Euler cycle is harder. And I really thought that these two are very similar. But actually, there's a very simple way to find Euler cycle. But for Hamiltonian cycle, I have to brute force it. And at any case, for both problems, if you do give me a solution, can I check it easily? Yes. With Euler cycle, right, give me the path. Then I'll just start and keep on going, and I'll get to the end and see if I end up with the same vertex and if I've been to every edge once. For Hamiltonian cycle, same thing. Give me the paths and I'll just follow it. Then let me see if I end up where I started and that I've been to every vertex once. Easy. You can do this in a polynomial time, like linear time, in fact. But see, this is why P versus NP is interesting, because these problems are very similar. I can do one in polynomial time. Why is it I can't do the other one in polynomial time as well? And also the fact that I can check the solution for both in polynomial time as well. So is there a way that I can do this in polynomial time? Is there a way I can solve the NP problems in polynomial time? Like the fact that I can check the solution in P time, is there a hint there that it can be done? Okay, so that's my attempt to relate P versus NP to you, to tell you why I find it interesting. Well, not just me, a lot of people find this interesting. And yeah, just to summarize, just one more time. We don't know if there is a polynomial time algorithm to solve the problems in P, but we can verify it in P. So it would be nice if we can find an algorithm would be. And just one more time to make sure that everything is clear to you. If Q is in NP, is Q also in EXP? The answer is yes. Because the problems that in NP, you can actually do them exponential time. So that's the brute force method of doing it. So if the problem is in NP, it is also in EXP. Now, if the problem is in P, is it also in NP? The answer is yes. If a problem Q is in P, then you can solve it in polynomial time. And what does being in NP means? Well, at least for now, we're going to say it's going to take more than polynomial time because we just don't know, right? We know we can do them in exponential time. So if you can do it in polynomial time, then yeah, it's in NP. Finally, if the problem is in NP, is it also in P? And that is the million-dollar question, literally. We want to know if the problems in the special class NP can be done in polynomial time. That's it. That's the whole idea behind P versus NP. So this is how I picture it in my head. Before NP came along, we have EXP and we have P, and we know how P relates to EXP. So we got a whole bunch of problems. Some of them you can do in polynomial time, and some you can't. Then NP came along, and it's like saying, "Hey guys, we got some problems here. We can't do them in polynomial time, but we can verify if they're correct in polynomial time." And these guys are special. So these problems in the red area, you can't even verify them in polynomial time. But these guys in NP, in the green area, you can. So that makes us think, well, does that mean these guys in NP, they're actually P? Is there a way we can do it in P? And people spend their lifetime trying to work this out. They're trying to work out if maybe NP is just P. As in all these problems in NP, they're actually just solvable in NP. We just don't know how to do it yet. Right, so that's I have that in writing here, and that's it. That's P versus NP. Now we're gonna talk more about this, but for now, make sure you're clear about the differences between these complexity classes. So you got P, EXP, and NP, and maybe sub EXP as well. Think about where it belongs. And one question you can ask yourself is, what do you have to do to prove that P is NP? Now, if you look back at the picture here, it kind of means that you have to show that every single NP problem can be solved in P time, which sounds insane. But we're gonna see how to do this. Well, no one has done it, but they have a plan. They know the way, and we're gonna see what they try to do. Okay, and we'll do that in the next lecture. I think we've done enough theory about P versus NP. So now I just want to talk about why you should care about P versus NP. All right, so me. Do I think that P is equal to NP? No. I think these NP guys are hard. I don't think you can do them in polynomial time. I think just about everybody I know also think that way. Are there people smarter than me who thinks that P is equal to NP? Yes. Something you can do is you can go to Google and you go look for survey P versus NP. And a bunch of computer scientists give their opinion on it. Now let's talk about you. Why should you care? Well, you should know that there are no efficient algorithms to solve an NP problem. So if you face an NP problem, don't try to find one. There will be other ways to handle that. We're going to be talking about approximation algorithms later. And hopefully you can also recognize NP problems. We're going to go through a few NP problems. But as you can see, two problems can be very, very similar. But they can be completely different in terms of complexity because one is in P and the other one is in NP. You saw that with the longest path and shortest path. You saw that with Euler cycle and Hamiltonian cycle. They're very similar, but they're worlds apart when it comes to solving them. And finally, what these 2 points boil down to is the cartoon that I had, I think, in the very first lecture that we had in this unit. This is a classic from a D book for complexity theory. So at work, you gotta be faced with a problem at times where you just don't know how to do it. You don't know how to do it in Parliament time. You don't know how to do it efficiently. And you can just go to your boss and say, look, I'm dumb, I can't do it. Or if you can recognize that this is an MP problem, you can tell your boss, look, I can't do it because it's not possible. At least people way smarter than me, people working in all this like computer science research and all these famous universities, they can't do it. So how do you expect me to do it? That's the thing, like all these great lecturers, all these great scientists, they can't do it. Well, I'm not saying that you can't do it. Maybe one day you work it out and you can get $1 million, which is sadly not worth that much these days. Can't even buy a house in Sydney. But yeah, that's why you should care about P versus NP. You should be able to recognize that some problems are just so hard that there is no efficient way to do it. And if you ever have to solve this kind of problem, well, you better find other ways to do it. Or just accept that this must be done using brute force. Okay? So, yeah, I think that's enough for one lecture. This is just a background still on P versus NP. The next one is also still a bit of a background because we're going to be talking about NP complete and NP hard. Then after that, we'll do reduction and then we'll do approximation algorithm, which is more practical. So, yep, I'll see you in the next lecture.